this set of videos I'm going to be explaining basically power conversion systems. I tried to record this once already, but it ended up devolving into me ranting on about like different semiconductor principles for about 13 minutes straight. I was thinking about editing it together and posting it anyway, because obviously I don't want to have to rant like that again. The only issue is that it cut off the top of my head right here and everything, so I just decided to re-record it. This I'll definitely try and keep more direction to. What we're specifically going to be looking at in this set of videos is DC-DC conversion, better known as switch mode controller tutorials, and topics like that. This because in the terms of power conversion, as far as how you would convert one voltage to another, there's been several methods. These range from the impractical to the just plain dumb to the very efficient. The very efficient being obviously your switching controllers, so you're bucking your boosting circuits, plus your half bridges and full bridges and your inverter based topologies. As far as the relatively impractical, you have the transformer and inverter based designs where you literally invert the signal to turn it back into AC. You ram it through a transformer to convert the step ratio and the turns ratio, and then you rectify right back into DC. Now that works, and if you have everything considered, you can adjust a number of parameters to get the same output. The only problem is that, first of all, it's extremely inefficient, because you have to convert one voltage into AC, then jam it through a transformer, which is inherently lossy. Obviously nothing can perform like an ideal transformer. Then you have to induce losses in the rectification diodes to convert right back to DC, and then you have to filter and reduce ripple and everything. Plus, transformers were never exactly the best option because of the fact that they are sized linearly to their power. They're not like, your average transistor, where a transistor that's, half the size of your pinky nail can dissipate a few watts. The transistor the size of your full pinky nail can dissipate, 100 to 250. No, that's not the case. Transformers are very much sized to their power level, and so to get a system capable of providing 12 volts at 100 amps, you would need a ridiculously large transformer. So that's where the switch mode stuff comes in. And this is a range of continuing necessity in the industry. In fact, if you want to see your average bucking controller and bucking circuit and stuff like that, you can look on your average computer motherboard and you'll see at least 3 of these. You'll see the smoothing capacitors, you'll see the tank coils, the diodes, and the transistors, the power MOSFETs. They're designed to switch this. You can basically separate the circuit into 2 different components. The first is the switching component, and oddly enough, in a lot of contexts, the diode is considered to be part of the switch because of how it interoperates with the transistor. And that's why a lot of the times when diodes are specified in these circuits, they're designed to be hyper-fast switching diodes. That's not necessarily because the diode does anything, but it's because how it interoperates. And finally, the coil, the inductor. Now, for most part, we're going to act like this smoothing capacitor doesn't exist, because you're still going to produce the output without it. It doesn't directly affect the output. It affects the voltage ripple and the frequency component of the output. So it essentially just gives you a cleaner signal, but it doesn't actually impart anything to the circuit that you otherwise wouldn't be able to get. The inductor is what actually stores your energy. Now, this is essentially an electric version of a flywheel. What happens is your transistor pops on and it constantly loads energy into this inductor, and the energy comes out during different parts of the cycle. I mean, I'm drawing a blank on the exact description. I mean, I know how it works, but as I said, I'm drawing a blank on the exact mechanism of how that works. But the idea is that by changing around the duty cycle of this input switch, essentially the ratio of how long it's on to how long it's off, you can control the voltage output, where your voltage output is any multiple of your voltage input by way of duty cycle. Boost controllers and boost circuits are another sort of thing, but I'm not going to spend any time going into that because the boost topology is pretty much a buck topology, except you pretty much switch around a few components. You have your inductor where the switch is, your switch where the diode is, and the diode, you essentially go full circle. In fact, a lot of the design equations for boost circuits are very comparable as well. It's just a matter of what goes where. The only thing that really changes is the duty cycle derivation, but for the most part, it's the same. That being said, in the next video, I'm going to try and make this into a bunch of different parts because my camera can only record for 10 minutes straight. The second part, the next part I'm going to do is going to be on inverter-based systems, so your half and your full bridge systems, your true AC converters. And finally, the last part is going to be a bunch of rambling about how the actual semiconductors function, the difference between them. So what an IGBT is versus a power MOSFET, stuff of that nature. Alright, well, as is typical for my videos, if you decide you hate this, tell me in the comments. Like, subscribe, do all your stuff. Read the description. I usually put important stuff in the description. And yeah.